this computer. We will start today's lecture with a follow-up of what we drive last time. And essentially, we will be closing the second quantization, and we will be entering to the part that we talk about photon statistic, which is extremely important. I mean, when you talk to the, let's say, orthodox quantum optics people, they talk about sub-Poissonian, super Poissonian, Poissonian distribution, or Maxwell distribution, and etc. So today we will talk about that, and we will have, let's say, the tools and understanding the states. And next lecture, which will be after this reading week, we will go with the Q, P, and Wigner representation, and then that's the final point, and we will close that part, and we will start, let's say, with the G2 function, Gn function, and the optical elements action in the quantum optics regime. So I'm sure that you heard of Hongou-Mandel effect, photon bunching, anti-bunching states, and etc. So we will discuss about that, about those scenarios during next 3 lectures. And finally, we will talk about new phenomena, let's say not new phenomena, those effects or observation that people they used, and some of the people even they got Nobel Prizes for some of those observations, like Humphrey, Brown, and Twiss. And then we will go with some of the key essential experiments, like induced coherent spontaneous parametric Dunn conversion. And finally, we will close everything with some of the technological applications. So two of my colleagues, I would call them nowadays, I mean, starting from last year, I would call them my colleagues. Frederick Bouchard will give you a lecture about quantum key distribution, okay, which will be one of the application of quantum optics. This is what people they use. It will be, I have not yet made a decision, so maybe it will be 1 hour and 30 minutes, or maybe it will be a full 3 hours, depending on how deep we want to go into the field of, let's say, quantum communication. And one of my senior postdoc also, he will give a lecture about spontaneous parametric Dunn conversion and photon correlation. So for those people, they have been in my team, like Florence, I think she's here. Whom else? Oh, Felix as well. I gave 5 lectures on just talking about spontaneous parametric Dunn conversion, and Manuel as well. So it's a subject which can go really deep, but I would say that it's something that you will need it. So I will ask Alessio to give a 3-hour lecture based on lecture notes that I passed to him, and also some new experimental result that he has. So that's just a roadmap. So I understand that the lecture is a little bit slow. I'm sorry for that, because it's Zoom. First of all, is from the distance, is not in the classroom that we can receive feedback from each other. But soon, let's say next lecture will be really faster. Okay. So if there is no question, we will start with a follow-up of our discussion. So let me share the screen. Start broadcasting. Okay. Okay, excellent. So far, we learned how to do the quantization of the field. And one thing that we understood is that it is unbelievably, I would say, not easy, but unbelievably surprising that when we did the field quantization, we got modes to be similar to those that we have it in the simple harmonic oscillator. And that was a surprise, I would say. And then we got familiar with the action of vacuum. we tried to look into two different cases. One was a Casimir effect. The other one was a Lamb shift. And we understood that this second quantization essentially is true. So it's not really just mathematical tools that you want to have some sort of representation for EM field. So hereafter, what we go with some sort of properties, finding the property and features for the states. So we work on specific states. So just to recall, because I always prefer to start from beginning, so recall that we deal with annihilation creation operators. So annihilation and creation operator, they were given by 1 divided by square root of 2m h bar omega and m omega q plus p plus ip. And the other one, creation operator, was given by 1 divided by square root of 2m h bar omega of m omega q minus ip. Excellent. So we had this, and we of course knew that Hamiltonian that we had p2 divided by 2m plus 1/2 of m omega square q square was diagonalized in bases which we had n states. And n essentially was eigenstate of n operator, which n operator was A dagger A. And remember, we are working only on one single mode now. That is true that we are talking about harmonic oscillator, simple harmonic oscillator, but essentially we got the relation between EM field and when we did the quantization. So these look like one specific mode. So we don't talk about the polarization. We don't talk about K vector as well. So we assume that K vector and polarization is fixed. Good. And then we say that A acting on N will give you square root of N times N minus 1. And A dagger acting on N was N plus 1, N plus 1. All right, I think hopefully this time I didn't do any mistake. Right, Henry? Good, excellent. So far, so good. Let's do a little bit of mathematics, okay? Remember, when we talk about n state, we assume that you have, I mean, the energy that we had it for this, H acting on N was H bar omega N plus 1 times N. So this was the eigenenergy. Okay, associated with state of N. Can someone tell me what is the state of N at any given time of t? I think Josh wants to speak.
Yeah, e to the I h bar omega n plus 1/2 t. N plus 1/2 in brackets t.
Times t divided by I, should I say?
Oh, divided by h bar.
H bar with a negative sign.
Yeah, right.
Of course, acting on N. So this is what we have from Schrödinger equation. As a state at any time, a given time of t. So you may ask me, for example, how did I find this? For example, David, can you make a guess and tell me how did I find this? Right? Using the Schrödinger equation. So we had n at t is equal to Hamiltonian acting at n in the time of t, right? So when you do the exponential, then you will find out that at any given time of t, this n is given by this expression. All right? No questions? So far, I think we are in agreement. Remember, if I have an arbitrary state of psi, so sub psi is a state which is given at the time equal to 0, and this arbitrary in this state is a superposition of n at time equal to 0. Okay, can I write that? So I define that if you remember that, let's say this is the potential that we had for simple harmonic oscillator. So the potential was quadratic. And these were the states. So the first state was here. The second state was here. The third state was here, and etc. So this was n equal to 0, ground state, n equal to 1, n equal to 2, n equal to 3. And each of them, they have specific, let's say, wave function. Let's call them n or 0, which is vacuum. This is 1, this is 2, this is 3. So now I built up a wave function. With this wave function, place a coefficient for each of those. So C0, C1, C2, C3, and until Cn, which the states are unbounded, by the way. Remember that it goes to infinity. Then I assume that I create a specific state, which is coherent superposition of all of them. All right? So now this state of psi at time equal to 0, if I leave it and let it propagate, or let's let it evolve in time, then you will get psi at time of t, which essentially is given exactly with that expression. So it will be summation or n that is starts from 0 to infinity. Then it goes with e power of minus I n plus 1 divided by 2 omega t times n at time of 0. And of course, I do have this coefficient of Cn. All right? Good? Okay, excellent. So just to have a feeling what we are dealing with, so we are dealing with this case. All right. Now, I assume a pure Fock state. What I mean, so there is no superposition. There is no superposition state. What I have only state of n. Good. As a question, since we deal with quantum mechanics and quantum optics, we want to understand what's going on with statistic, let's say not statistic, with the variation of operators that we deal with. So for this case of simple harmonic oscillators, we deal with X and let's say Q and P, right? So what we have Q and we have P, which there are two observables. Remember that A and A dagger, they are not observables because they are not Hermitian. But instead, what we have Q and P, which they are look like canonical position and canonical momentum, they are observables. Okay. So in the case of, let's say, simple harmonic, this is essentially X and P. And we know very well, and we recall very well that the commutation between Q and P, they were not equal to 0. So they were non-vanishing terms. All right. So what I want to do, I want to look at uncertainty relation between Q and P. So what is the relation between Q and P? And I don't want to look at the commutation relation between these two. I look at the variance of them. Delta P squared. Okay. from statistic, we remember that what was the definition for delta Q? Was Q squared minus Q squared. This is the variance. Now let us do the calculation for Q and Q squared. You may ask me why I place a bracket here, because of course this is the definition of the variance, but you have to do the variance for specific statistic, right? So you have to do it for specific state. And this indicates that we are doing for a specific one. So here in this concept, I am doing, we calculate the variances for a pure Fock state. All right. Okay, let's do that. So first of all, we will do it for Q, and then we'll do it for Q squared. What is Q? Look at the definition of annihilation creation operator, the one that I highlighted with yellow. You want to find Q. What is Q? Is a summation of A and A dagger with a coefficient. Let's do that. So Q is essentially is M omega. It will be 2M omega. Okay, so it will be square root of 2M H bar omega divided by 2M omega. A plus A dagger. And what about Q and what about P? P essentially is with minus I, so it will be A minus A dagger. It will be square root of 2M H bar omega divided by 2I M. Oh, no, there is no M. Good. And I have A minus A dagger. All right. I don't think that if there is any mistake, please let me know. No, all right, good. Okay. Let's simplify a little bit. So we get square root of H bar divided by 2M omega of A plus A dagger. And that will be minus I square root of M H bar omega divided by 2. Okay. Just remember, because later on we will be using it, people, they prefer to work in a dimensionless coordinate. So what they do, they look at the Q divided by square root of H bar divided by 2M omega. Let me see if it's that one. I will write it in a proper way, by the way. They call this X. Okay. Or also they look at the P divided by square root of M H bar omega divided by 2 minus I divided by 2 of A minus A dagger. They call also Y. Let's go with, since we go with the quadrature form, let's call this one X1 and let's call that one X2. Okay. This is the definition that people usually they prefer to work with. Is a dimensionless, or is in unit of the coefficient that we deal with. Good. Okay, excellent. So let's work in the dimensionless situation. So let's call X1, which is 1 divided by 2 of A plus A dagger. And we have X2, which is 1 divided by 2. Sorry, minus I divided by 2, A minus A dagger. Okay. First of all, are they observables? Are they Hermitian? Yes. Look at, exactly. Look at the X1 dagger, and you will see that, yes, it is Hermitian. Look at the X2 dagger, you will see that, again, also this is Hermitian. So both X1 and X2 are observables, which is look like what we have as X and P. Okay, it's Q and P. It's canonical momentum and canonical position. Not a surprise. Okay. Good.
What do you mean by canonical, may I ask?
So not necessary that look, we associated these to be similar to the simple harmonic oscillators. But in reality, these X and X1 and X2 or Q1 and Q2, they are not position and momentum in real space. Okay, by this means. Not that P is replaced by P minus EA. That's a canonical momentum. Okay. Good. Okay. So now I look at, instead of looking for delta Q square, I'm looking at delta X1 square, which X1 is that operator that I define here. So this means that it's X1 power of 2 minus X1 power of 2. All right. Now let's do the variance in the Folk state spaces. First of all, let's do that. Okay, so it means that you have the variance of n e power of I n plus 1 h bar omega x1 power of 2 e power of minus I n plus 1 h bar omega acting on iron minus the other term, or let's write it down here. Do you agree? Okay. Okay. So indeed, we deal with Q, which Q is given by n e power of, we can simplify that. So by the way, is there any question here? So how I replace this, or is clear? No questions? You can raise your hand if you have. Okay.
I'm missing a T.
Oh, yes, sorry.
Many.
Yeah, all of them, they are T.
I think no H bar. Oh, yeah.
Yeah, omega T. Thank you very much. Yes, is omega T. Okay, good. So,
and the n here in the exponent is a constant, not an operator.
No, it's exactly is a constant, is not an operator, because if you remember, this is what we had it here. Right?
Yeah.
Okay, or
yeah.
here.
Yeah, perfect.
Excellent. Even if it's n operator, then will act on the state, and then that will give you a constant of n. So let's do a little bit of let's simplify this. So I will do it. Okay. So the exponential terms, they are conjugate of each other, so they will go away. Then you will have 1 divided by 2 of n acting on a plus a dagger on n. So that is 1 divided by 2. So Felix, can you tell me the result?
So we will get root n plus.
So a dagger acting on n will give you square root of n plus 1, and then you will get n plus 1, right? Then you will have, okay, let's do that.
Yeah.
So you will get n, and from a you will get n, and from the other one you will get n plus 1. Do you agree?
Yeah.
What's the result?
So 0.
Is 0. Excellent. What about q squared? For q squared, you will get 1 divided by 4 n a plus a dagger a plus a dagger of n. So you will get 1 divided by 4. You have 4 terms essentially. You will get a dagger plus a dagger a, and plus a dagger acting on n. So from the same physics, we know very well that these results in 0, these result in 0. The only 2 terms that they will remain, they are this one and that one. All right? So then we will get 1 divided by 4. And a dagger, you can write it in the order way. So that can be from, we know that a and a dagger is equal to 1. So a dagger minus a dagger a is equal to 1. So whenever we have a dagger, that can be replaced by 1 plus a dagger a. So that can be replaced by 1 plus a dagger A. So that can be written as n 2a dagger A plus 1 acting on n. Okay, which is 1 divided by 4, and that is 2n plus 1. Good. Let's do that also for delta x2. And by the way, this is what we had. My apologies. It shouldn't be q. It should be x1 and x1 power of 2. So then delta x1 power of 2 essentially is given by 1 divided by 2, 1 divided by 4 of 2n plus 1. This is the variance that we have it on, let's say, x-like operator. Let's do that for delta x2 power of 2, which is essentially x2 power of 2 minus x2 power of 2. So we have to do the calculation for x2 power of x2, which is essentially n exponential of minus plus I n plus 1/2 of omega t. And then what else we have? We have x2. x2 is 1 divided by 2i of a minus a dagger, acting on e power of I n plus 1/2 of omega t with a negative sign acting on n. And we know very well with a similar, in a similar fashion, we can prove that that will be 1 divided by 2i n a minus a dagger acting on n, and we know very well this is equal to 0. And let's do that for x2 power of 2, which x2 power of 2 will be given by n. I will just simplify that. Minus 1 divided by 4 on a minus a dagger acting on a minus a dagger on n. So let's do the math. We'll get minus 1 divided by 4 and a minus a dagger minus a dagger a plus a dagger acting on n. So this is in a similar way. We know very well that these two terms, they will remain. The other two terms will be 0. And finally, we'll get 1 divided by 4. That one also should be replaced by a dagger a plus 1. So that is 2n plus 1. So essentially, you could have done that at the time equal to 0, not dealing with any given time. It's just an exercise, just to understand better the situation. So from here, we get delta x2 power of 2 is 1 divided by 4 of 2n plus 1. So delta x1 we obtain which is 1 divided by 4 to n plus 1. And delta x2 power of 2 is 1 divided by 4 to n plus 1. So from these two relations, we find that delta x1, delta x2 is 1 divided by 4 to n plus 1, which is always greater than or equal to 1 divided by 4. All right. Who can interpret this expression? Remember that x1 and x2, they are look like momentum and position. Okay. So essentially, I can look at the, let's say, quadrature, or you can look at the phase space, essentially, when you have x1 and you do have x2. Can someone tell me what I am seeing?
You mean uncertainty or something like that?
Tell me what is the meaning of this expression. Let's highlight it.
So it means you're gonna have a circle around the origin.
How do we get a circle around the origin?
I don't know, I'm just spitballing here.
I will give you another hint.
Okay.
Look at the value of x2. Which is 0, right? Look at the expectation value of x1, which is 0. Okay? Tell me now.
So like the mean value for x1 and x2 are centered on 0.
Lovely. Exactly what you say also, Josh. So this is what you will have, is here, is at the 0. Is the expectation value exactly at the origin. For which distribution? Which state did we consider?
For a pure state?
Pure Fock state. Right? Or for number state of n. This is what you will get. You will get the average to be exactly at the origin. All right. Okay. What else? And by the way, we are working in a dimensionless coordinate, so we are fine with the value of x1 and x2, so is the same dimension. Whom else? Because this is important, I want you to reach to this point. Thomas, do you have any thoughts? your microphone is off, I think, is muted. Okay, doesn't matter. I will ask someone else until you will get your microphone on. So Henry.
We have a width, and at least for n equals 0, it would be a quarter.
So can you tell me more? Of course.
Well, we have the mean is 0, but now we have the variance. So
exactly.
there is a non-zero variance. So it's not a point. It has a width.
Lovely. Exactly is what you mentioned. So this is what happens. Of course, I mean, we do have a point, an average, but there is a variation, is jumping around, okay? And this variation has a width. Okay, now let's ask someone else. Yaswan?
Yeah.
Assume that n is equal to 0. Okay, can you elaborate and tell me more about what Henry mentioned? So we have x1, we have x2, the average is exactly at the origin, right?
So n is equal to 0 means you are at vacuum state. So because of the variance, you get 1/4.
Exactly. So delta x1 is 1 divided by 4, and delta x2 is 1 divided by 4, right? So it means that we have, if each two block here, each two blocks is 1 unit, then it means that the variance will be here and it will be here.
Aren't they like 1/2? Because it's the square root.
Yes, it will be one half, of course. So this is the reason I said it is 1/2. Okay, thank you, Manuel. So it is 1/2 here. So this is the variance that you have it here. And also along this, you have a variance. All right. So this is the region that you expect to have x1 and x2 around the origin. Manuel, since you speaked up, can you tell me about n equal to 2, n equal to 1? One single photon state.
Let me do the arithmetics.
Okay. So delta x1 power of 2 will be 1 divided by 4, 2 times 1, which will be plus 1, which will be 3. Delta x2 power of 2 will be the same, 3 divided by 4. Again, the average is where? Is at the origin.
Yep.
But what is happening? Instead of, let's say, being close by, now you have a spread in uncertainty here. So that goes to be 1 divided by square root of 3 divided by 2. Square root of 3 is 1.7. So essentially is 1.7. It's something like here.
Oh, it seems that we don't believe in irrational numbers.
Okay. This is the uncertainty that you will have.
I have a question.
Yes. And now I do have a question for you.
Oh,
Don't jump.
I mean, I have some feeling, but I mean, in these Fock states, it's like a step function. I mean, sometimes, I mean, it's just like an abrupt disappearing of the distribution.
You say that it looks like a step function, yeah. And sometimes what we have
in this circle version of the distribution is like a disk of, let's call like a region where it exists and the rest is 0. It's completely like just abrupt.
So look, we will come back to this, why we have this uncertainty here. This comes from uncertainty relation that you have it between number state and the phase. So this is the freedom that you have it on the phase of single photon. Okay, is a very fundamental problem.
But yeah, but I mean, for the Fock state, is it just like an abrupt? For example, if I go, for example, for the case of of zero state, if I go outside, like I don't know, like to 2, I mean, it's totally improbable that I will find my. I mean, there's no relationship. It's just abrupt. It's like not a smooth function.
Yeah, no. It's a distribution. This is a variance.
Yeah, but
this is a variance. So you have a distribution along this. Okay.
Yeah, but these are distribution only in the radii of the circle. Am I right? Outside it's 0.
Yeah, it is. It's not squeezed. It's not, let's say, deformed.
Okay, it's just like a piecewise function.
Yeah.
Okay. Yeah, that was my question.
Okay.
Now your question.
Good. So what is happening now? I mean, if I increase n, the uncertainty relation will be higher and higher. Okay, so then it means that I don't have too much information about what is x and what is the value of x2. Okay, the precision that I have in the measurement. So can you tell me what is the minimum value that I have? Manuel.
The minimum value for
uncertainty relation
is 1/4.
Which is for?
The vacuum state.
For vacuum state. Okay, lovely. Okay, good. So far, so good. Is there any question? No? Excellent. Now let's go up. Now I can build up whatever I want, right? I can go with any state that I want. I can go with any state that I wish and you wanted me to build up. Okay, let's go with which state? If I want, let's build up something new.
What about?
I will do it for a specific state. Then I will give you an assignment for yourself that go home and work on another one. Okay, I can look at. We love to work with mathematics, and sometimes later on we will find a concept for it. Let's build up an operator. All right, so this operator has specific property. Sorry, we have a state which this state has a specific property. The state alpha I introduce. Let us introduce alpha such a way that A acting on alpha is alpha A. Alpha. So essentially what I mean, the state of alpha is eigenstate of annihilation operator. Good? Good. So alpha is the eigenstate of annihilation operator.
So this would just be the vacuum state for alpha equals 0? If alpha equals 0?
No, not necessary. Alpha is not 0.
Okay. Yeah, but
okay?
if we take alpha
if it's
0,
0, then essentially you will get the same result as you mentioned. So A acting on vacuum will be vacuum, right?
Okay.
So an alpha essentially is an element of complex variables. So alpha has a real part and also an imaginary part, or let's say a phase, which means that alpha is given by alpha e power of I. What should I call it? Theta? Phi? Whatever. Yes, let's call it. I use chi phi. Remember, phi is not a coordinate, it's just an angle. Okay. Alpha and absolute value, of course, we know, and alpha is a phase. Good. Do we? I think we all agree that n state, the Fock states, they were complete bases. All right. So it means that summation on n from 0 to infinity, acting on n, was 1. Do you agree?
Mhm.
Okay, beautiful. Then we can expand alpha in terms of n, which what we discussed. So it was Cn n. For the discussion that we had, I mean, that was the reason that for the previous case, I look at the time evolution, okay? And hereafter, I'm not looking at the time evolution because I know that in any cases, they will sum up and they will be okay. So we will look in that if you wish later on. So alpha essentially can be expanded in terms of Fock states with the coefficient of Cn, which we have no clue so far that Cn must be found. So we have no clue about Cn, the coefficient of expansions. But what we know that alpha should have this property. All right?
Mhm.
Good. So let's replace it here. So we say that A acting on alpha must give us alpha on alpha. And alpha is a summation of Cn acting on n from 0 to infinity. And again, that will be summation of Cn acting on n from 0 to infinity. Therefore, we have A acting on Cn and alpha summation on n equal to 0 to infinity of Cn. Good. So A will act on n, and A acting on n will give us square root of n minus 1. And for sure, we know that then this cannot take negative value. Therefore, n should start from 1. And then I have alpha, summation of n from 0 to infinity of Cn n. Good?
Mhm.
Excellent. So, and we know very well that n's are orthogonal to each other. So, bra of m, ket of n is delta of mn. So there is no way that I can expand state of 1 in terms of state of 2, 3, or the rest. So they are orthogonal to each other. Therefore, the two sides of these, they must be equal for identical photon numbers. Okay? Then since I know that, and we know that n are orthogonal and complete basis, then what I do, I will change the summation, or let's say n minus 1 to, let's go with a new variable of m. So n minus 1 is equal to m. Then the summation will change from m equal to 0 to infinity. So n is equal to n plus 1. So that will be Cn plus 1, square root of m plus 1. And then that will be m equal to alpha summation of, now I can change also that to be m. So m from 0 to infinity, Cn of m. For this case, n is equal to n. All right. Now, each m from the two sides, they should have the same coefficient, which means that Cm Cm plus 1 square root of m plus 1 must be equal to alpha Cm. And therefore, Cm plus 1 is equal to alpha divided by square root of m plus 1 Cm. I found the recursion relations between the coefficients. And essentially from this term, easily I can find that Cm is equal to alpha power of m divided by square root of m factorial times C0, which C0 is just a constant. Anyone having problem with this, or should I expand it? Clear? Please speak out if you have problem.
I have a question.
Yes.
Like, why I have a question. Why on the right hand side we treat m equal to n, while on the left hand side we treat m is equal to n minus 1?
Because I want both to have the same Kate state. So if we look at that one, right? Let me erase this. The Kate, now it starts from n minus 1, right?
Yeah.
Okay. And here it starts from n.
Yeah.
I cannot say that these two, they're identical.
That's true.
Right? So, but I know, let's do the expansions. And I think you will get that. So let's do the expansions. And I know that Cn, n equal to 1 of infinity, Cn square root of n, n minus 1, equal to alpha summation of n equal to 0 to infinity, Cn n. Let's expand the right-hand side and left-hand side, both of them. I don't see Caesarea. Okay, yes, I do see it. So from here, the first one will be starting from 1, right? It will be C1 square root of 1, 1 minus 1, which is 0.
Yeah.
Okay. Then for the other one, what is happening? It will be C2 square root of 2, 1. C3 square root of 3, 2. Plus other term. What about the other side? We have alpha C0, 0, plus alpha C1, 1, plus alpha C2, 2, and etc. Look, now I can say that 0 must be equal to 0, the coefficients, because they are orthogonal to each other. 1 should be equal to 1, 2 should be equal to 2, and etc. So with the trick that I have done that, essentially in a mathematical form, I made both of them to be equal to m, because there is they don't start, essentially they start from the same value of 0, but when I look at the mathematical form, one of them has n minus 1, the other one has n. So what I should do, I should make both of them to be starting from the same sum, which is n equal to 1 or n equal to 0 for both of them. This is the reason that I have done that change. Essentially, what I want to do, I want to have the Kate of m without anything else appearing in both sides. Then it is very easy for me saying that, yes, left-hand side of m should be equal to right side of m as well. Since both summation, they start from, let's say, 0. Okay? Good? Okay. So then I have Cm, which is equal to alpha power of m divided by square root of m factorial of C0. So I found the coefficient. What was the state? Remember. This is the state. And alpha was summation of n equal to 0 to infinity of Cn n. And from the above relation, I found that this is given by C0 alpha power of n divided by square root of n factorial. Good? I think it's clear. Do we know the state of alpha now? Not yet. What is missing?
C0?
C0. Yeah. Still, I don't know what is C0. Good. Do we agree that alpha should be normalized? We work with normalized functions. So let's make it normalized to be equal to 1. Then what does it mean that we have summation of n equal to 0, Cn. Now let's go with explicit expression, C0 star alpha star power of n divided by square root of n factorial. Then that is n summation on m from 0 to infinity of C0 alpha power of m divided by square root of m factorial ket of m. Or essentially, we will have summation of m from 0 to infinity, summation of n from 0 to infinity of C0 power of 2, alpha star power of n, alpha power of m divided by square root of n factorial, n factorial, n and m, which this is equal to delta of m and n. Which the delta Kronecker, when you have two summations, one of them will go everywhere. This delta is 0 except the places with m is equal to n. Then we get summation of m equal to 0 to infinity of C0 power of 2 alpha absolute value power of m divided by m factorial, because n is equal to m now.
Wouldn't it be alpha power of 2m? Alpha absolute value power of 2m?
Pardon?
The alpha to the power of m?
Yes, it's
okay.
2m. Yeah. Thank you. All right. And from here, we get C0 power of 2 summation on alpha power of 2m divided by m factorial. M star from 0 to infinity. Let's ask Tenlu. Tenlu, can you tell me what is this? If you don't know, that's fine. I mean,
Does it look like an exponent or?
Yeah, exponential of
alpha? Is it called alpha? Yeah, it should be alpha. Alpha
power of 2. Power of 2. Exactly. So then this is equal to 1, right? This is the normalization coefficient. So therefore, we got C0 equal to e power of minus 1 alpha divided by 2 divided by 2. Alpha power of 2 divided by 2. Okay. We assume that is we assume that is a real quantity. So then, therefore, the state of alpha, which is e power of minus 1/2 of alpha squared summation on alpha power of n divided by square root of n factorial acting on n and changing from 0 to infinity, has the following property. which is eigenstate of annihilation operator. Okay. Good. We call alpha state coherent state. And we will see why we call it coherent state. Let's a little bit understand, I mean, so far it's just mathematical, abstract mathematics that we obtained. So that we started with the annihilation operator and we say they look for eigenstate of the annihilation operator, and from this we found the state. All right. What are the properties of coherent state? Do the mathematics and find out what is alpha times beta, which there are two coherent states, two different coherent states, which alpha is given by the above expression and beta is given by similar expression. Okay. It will be similar to what I have done previously. Valerio, are you doing the mathematics?
No, not yet.
Yes, please.
Yeah.
Also, I'm doing with you, guys. So I will do it. We will do it together. Okay. Do you agree? So the summation will give you exponential of alpha star b. And when you do, of course, remember alpha and b, they are beta and they are parameters. If you sum them up together, you will get alpha minus b beta power of 2. Okay. So what is the conclusion that, yes?
I have a question. How did you get to the last line. Because wouldn't the expansion of alpha minus
Let's do that. Let's do that. It will be
betas-
alpha star
Mhm.
plus beta star plus 2 alpha star, sorry, with the negative minus 2 alpha star beta. Do you agree with
Well,
that?
wouldn't there be a term? Wouldn't there be a term beta star alpha?
How do I get the beta star alpha?
Because the alpha minus beta absolute value squared, that's alpha star minus beta star times alpha minus beta. So wouldn't it be alpha alpha star plus beta beta star minus alpha star beta minus beta star alpha?
Okay, so the point, I mean, the point is that these two states of alpha and beta, the two coherent states, now they are not orthogonal, so the outcome is not 0. All right, because that's given by an exponential term. So when this exponential term will be 0?
Only where alpha and beta are the same.
When alpha beta they are the same, that will be 0, Manuel?
No, never.
If alpha is equal to beta, then that will be equal to 1. That's the orthonormality. Is not this is the normalization. It's not strange. When that will be 0?
Alpha minus beta is very big, goes to infinity.
Yeah. When alpha minus beta, they are really far away from each other. Alpha minus beta is big, or alpha is far away from beta, then these two, they will be equal to 0. Okay? So, and something else. So we know that alpha, or set of alpha, they are not orthogonal. Are they complete bases? Can we expand any photonic distribution or photons distribution in terms of alpha? Yes or no?
Yes.
How? The answer is yes. Let me see who was Josh.
Yeah. So because they are made up of Fock states and Fock states are a complete basis, then that's why.
I love your interpretation. Yes, exactly. Alphas are complete bases. Why? Because they are expanding in terms of n. And let's prove that. Okay? Let's do the calculation of alpha times alpha. Okay? We have to do the summation. And alpha is a continuous parameter, is a complex quantity. So we have to do the integration on alpha. Okay? So that is integral of d alpha. And remember, alpha has two integrals inside. One is on the either on the phase, the other one is on the magnitude, or on, let's say, real part and imaginary part. And alpha is given by e power of -1 divided by 2 of alpha squared, summation of n equal to 0 to infinity of alpha power of n divided by square root of n factorial of n. And then we have the other term, which is e power of 1 divided by alpha minus 1 divided by alpha power of 2 summation on n equal to 0 to, let's say m equal to 0 to infinity. Is the same, sorry. Yeah. Okay, m equal to 0 to infinity of alpha star power of m divided by m factorial square root of 2, and then we have m. All right. Are we fine with this, or do you have any problem? Good. Okay. Then we do have e power of minus alpha squared. Summation on n equal to 0 to infinity, alpha power of n, alpha star power of m, divided by square root of n factorial, m factorial. Then we do have, that is also on m and n. We do have n and m. Good. Any thoughts?
Go to polar coordinates?
What?
We could go to polar coordinates
Going to polar coordinate?
to integrate alpha, because it seems like it'll be easier to take out the phase from the product.
Yes. Yes. Excellent. If you do that, so if you go to the polar coordinate, you have to swap the integral with the summation. So that goes to m from infinity. Then you do have integral of d alpha, e power of minus alpha squared. And then you do have alpha power of n, alpha star power of m, divided by square root of n factorial, square root of m factorial. This is the expression that you have it, and then you have n and m. All right? And these integrals should be calculated. As Eric says, there are two different ways that you can solve that. Either going to, let's say, because the alpha, remember, alpha has alpha and e power of I think phi, I assume. You can do this integral. So you have to do the integration on phi. You have to do the integration on alpha. And that will give you a delta function, delta of one term, m and n, with the coefficient. Do that at home. And finally, what you will get with, I think there is an exponential term that appears, so 1 divided by pi, or something like that, I don't remember. Because it's a Gaussian integral. It should be pi integral, pi here appearing. And then with the coefficient times n and n. And changing from 0 to infinity. So essentially, that will be pi times the coefficient summation of n from 0 to infinity, and that will be n and n, which is pi times identity. So it shows that the coherent states, they are complete bases. Let me look at my notes. I think I have written somewhere the explicit expression for alpha. Yeah, there is no other things, it's only pi. Okay. Then the completeness relation is given by integral of 1 divided by pi of d alpha 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 equal to 1. So coherent states are complete bases. Are they orthogonal? No, not orthogonal. So if a state is not orthogonal, is not complete, what we call it? We call them over complete bases. Coherent state is an over complete basis. Okay. I will give you a break and then come back, please. So how many minutes, guys? 4:10 is fine, or is too short?
10.
4:10. See you at 4:10 on this computer. I hope that you had a nice break. So let's share the screen. Good. So this was the relation that I mentioned that we should correct it. So let's place an absolute value here. And I think we are okay. All right. We place an absolute value here and then it should be fine. Good. So then so far, I mean, we learned that we have a specific state. I mean, I did not discuss about that, how to create this state. I mean, it's just mathematics. So which we call it coherent state, and this coherent state is given by exponential minus alpha divided by 2, to power of 2 divided by 2, summation on from n equal to 0 to infinity. And then we have alpha power of n divided by square root of n factorial acting on n. So look at the probability relation of this. So this is the state, and we call it coherent state, has a specific property. They are all complete bases. So it means that any function, although they are not orthogonal, any function can be expanded in terms of those functions. And this is very important. Remember that A acting on alpha is alpha alpha. Or for physics, because physics usually asks this question, what is happening if you have A dagger acting on alpha, which is alpha alpha star. Good.
Thank you.
Pardon? Good.
Thank you.
Fantastic. Okay. This is a probability distribution. All right. So it means that we have, do you remember this parabolic well that we had? And we say that is the, if we start from 0, that is n equal to 0, that is n equal to 1, n equal to 2. Sorry, guys, for repeating this stuff, but it helps us really to understand. N equal to 3, and n equal to 4, etc. This goes back also to Manuel's question that, I mean, some part of Manuel's question that he asked. First of all, I mean, alpha can be real and complex, or can be, in general, it's a complex quantity. Can you tell me what is the probability of finding alpha in photon state of n. We are looking for that probability. All right. So Josh, can you tell me?
Yeah, it's the absolute magnitude of yes, the absolute magnitude of alpha to the n over the square root of n factorial times e to the negative absolute alpha squared over 2. That absolute value all squared.
I have already done the square.
Oh yeah, okay, yeah. Sorry, I wasn't even watching what you were writing. Sorry. Yeah.
Check out if you agree with this.
Yes.
Okay.
Wait, the alpha in the exponential should be squared.
Oh yes, thank you. Lovely. Good catch. So do you agree, all guys, with this? So let's go with Manuel. Manuel, alpha can be any real quantity, any complex quantity. And we know here the magnitude plays role. So in this probability, let's say expression, you have magnitude of alpha, which makes sense, of course. So is alpha an arbitrary, let's say, parameter? Is it an arbitrary parameter?
Yes.
Okay, alpha is arbitrary, which we call it coherent parameter. And later on, you will understand that there is a physical phenomena that can do this job for us. And alpha is given by the, let's say, the coupling of these phenomena, okay? So alpha is a coherent parameter. Good. So tell me a number, right? It can be, we can plug any numbers that we want. So let's say alpha is equal to 0, then it is a vacuum, but we don't care about that. Alpha is equal to, let's say, 2, right? I'm choosing the parameter of alpha equal to 2, or it can be even a continuous, let's say, not necessarily integer, but let's choose alpha equal to 2, okay? Do you have any problem, Manuel, with that? No, okay. Alpha set to be equal to 2, so probability of finding it at the photon state of n is given by this expression, so is e power of 4, right? 4 power of n divided by n factorial. Agreed?
Mm-hmm.
Lovely. So can you tell me then what is this expression for these 4 or 5 states? N equal to 0. When we set n equal to 0, that will be e power of minus 4. 4 power of 0, which is 1, divided by 0 factorial, that is 1. The other one will be e power of minus 4. Then the other one, it will be 4 power of 2. Sorry, 4 power of 1 divided by 1 factorial. That it is n equal to 1, n equal to 2, n equal to 3, n equal to 3, 4. So each power of minus 4, 4 power of 2 divided by 2 factorial, e power of minus 4, 4 power of 3 divided by 3 factorial, e power of minus 4, 4 power of 4 divided by 4 factorial. Okay, so can I don't care about e power of minus 4 because it looks like a normalization factor, which essentially is a normalization factor. I care about the expression here. So this is 4, this is 1. What is this expression? Is 16 divided by 2, which is 8. What about this one? 64 divided by 6. Someone can do the math, guys?
$10.9-ish.
10.9-ish.
Mm-hmm.
What about this one?
4 power to 364. Oh, no, forget it.
4 power of 4
It's
divided
the
by
same as the previous one.
is 10.9. Because 4 goes away, it will be exactly the same value. So, and n equal to 5, n equal to 6. Just look at that values as well. So that will be e power of minus 4, 4 power of 5 divided by 5 factorial, e power of minus 4, 4 power of 6 divided by 6 factorial. Now you will see that it's decreasing the quantity. Can someone tell me the value? So 4 power of 5 divided by 5 factorial.
8.5.
8.5 makes sense. And the other one? 4 power of 6 divided by 6 factorial.
5.7.
5.7. Okay, good. And then, of course, decreasing. Manuel,
Yep.
can you do this math for n equal to 100?
Yeah, let me open something to do a calculation.
Even not 100, let's go with 20.
So it's, give me 2 minutes.
So it will be 4 power of 20 divided by 20 factorial.
Yeah. 4 power of 20 over
20 factorial.
Almost 0.
10 power of minus?
Minus 7. 4.5 power of minus 7. 10 to the
Minus
power.
7. Okay. So now, guys, look at the distribution. This is the photon number, right? And of course, photon number can take 0 value, 1 value, 2 value, 3, 4, 5, 6, 7, 8, 9, and etc. 0 has the probability of 1. This is 1 in unit of e power of minus 4. I'm plotting. Okay, so that has 1 unit, which is this. For 1, you have 4. 1, 2, 3, 4. So it goes up. So for 2 goes to 8. So this is 1, 2, 3, 4, 5, 6, 7, 8. It goes here. For 3 goes to 11. So until here it's 8, 9, 10, 11 goes here. For 4 goes to similar to 11. For 5 goes also to be equal to 8.35. It will be something like that. And then it goes on. For 6 goes to be 5.6. 1, 2, 3, 4, 5, 6 here. And then decreasing. So this is the distribution that you expect that happens. And at infinity, it decreases to 0. That was for n alpha equal to 2. Okay? Later on, you will see, we will see in a few minutes, alpha equal to 2 means that average photon number of 4. Okay? If you do the average for photon number, you will see that the photon number for the average of photon number, the mean photon number for this coherent state is given by essentially, let's do that, guys. Okay. It's simple. So let's look at average of n, which is n is operator, n operator for us is a photon number. Where we do, on which state we will do the mean photon number? On the state of coherent state, right? On the coherent state. So that means that it will be alpha acting on n operator of alpha, which is alpha acting on a dagger a, acting on alpha. And we know very well from the above expression that we have written here, alpha, a dagger acting on alpha will give us alpha star, and a acting on alpha will give us alpha, then it will be alpha squared. So essentially, mean photon number will be given by alpha squared. So essentially, for alpha equal to 2 means that the mean photon number is equal to 4. What you will get from these probability distribution for photon number? Look, we know from the, let's say this plot, we understand that probability on the photon number of this and that one is higher. 0, 1, 2, 3, and 4. So close to 3 and 4 is really high. So that tells us the probability distribution that you expect. So Manuel, after, let's say, certain quantity, this goes to be 0. Essentially, you are only picking up a certain photon number distribution. Essentially, you can almost neglect the region, the other regions. You can say that, okay, those photon numbers are extremely small. Okay, good. Now we look at the structure of these at the phase space. Of course, this was your question. So remember, if you look at the quantum well, or let's say this parabolic well, we know that the vacuum comes out with this coefficient, which is e power of -4, 1. For n equal to 1, it goes to be e power of -4 times 4. And n equal to 2, that will be e power of -4 times 8, and etc. Okay, so when we create these equal superposition, or let's say this superposition coherently, then we are dealing with a photonic statistic, which the statistic is given by this expression, is Poissonian distribution. And this Poissonian distribution has a form which depends on alpha. All right? And we already look at the average photon number, which is the average photon number is given by alpha squared. So means that close to 3 and 4, here we have the maximum value. Okay, so the probability of finding the the 4 photons is the highest compared to the rest. Of probability of n photon, which is equal to alpha square, is the highest probability that you may get. Okay, all right, guys. I think it's clear. If not, just let me know, then we can elaborate it a little bit more. Good. Now let me ask you another question. Do you remember our x1 and x2 operators, which was 1 divided by 2, a plus a dagger, and 1 divided by 2i, a minus a dagger? All right, I think that was the relation that we had for them. Now I'm asking you, for coherent state, for the above coherent state, find what is delta x1 power of 2 and delta x2 power of 2. I want to find the uncertainty principle in the phase space. Okay, for which state? Not for Fock states, but for coherent state. Try to do it by yourself, please. So what we are doing as a calculation, delta x1, for example, power of 2, we do the calculation of x1 power of 2 minus x1 power of 2.
At time 0 or at any time?
That's an excellent question. Okay. Do it at any given time.
All right.
That's a very important point, Eric. I'm doing with you guys. Okay, Manuel, you have a question?
Yeah, what happened when alpha is not, I mean, in this case, you choose 2. What if it's just like any number? I mean, because in this case, you're going to get like n, and it's going to be an integer because you chose 2. What happened if you chose something that is not an integer?
Absolutely. For example, you can choose alpha to be equal 0.5 or 0.1, right? First of all, we should agree that the absolute value of alpha is important for probability distribution. Do you agree with that? Okay, good. So you can choose alpha, absolute value is equal to 0.1. Okay, then you will have a statistic for photon. Not necessarily the statistic photon will match, let's say, an integer quantity. You will have the superposition, let's say equal probability for photon number of 2 and 3, photon number of 4 as well. So is the, let's say, the flat distribution. Okay. I'm doing with you, but let's do it together, okay? Who did the calculation?
I'm working on it.
Okay. I think I am done. Okay, let's look at the mathematics. Oh, someone texted me, sorry. Is it okay to, if I, okay, so guys, let's look at the mathematics. I'm sure that you have done, or you got the right track to do these simple mathematics. So essentially, we want to do the expectation value of x1 for the coherent state. So this is what we have to do, the mathematics. And for the time equal to 0, just to have a feeling what it will be the result for time equal to 0, then we get alpha acting an expectation value of A and expectation value of A dagger. All right. So which each of them, they will give us alpha and alpha star. So this is what we will get for the time equal to 0. Let's do it for any time of t. So for any time of t, alpha expression for alpha is this, right? In order to do the mathematics that we have here, let's do let's act A on alpha at the given time of t, which is which only A acts on n, not on the rest. When A acts on n, you will have square root of n, a ket of n minus 1. So the square root of n will be simplified with n factorial, then you will get square root of n minus 1 factorial. And of course, annihilates the state, so bring this 1 lower, so you will get n minus 1 as well. Okay, so the consequence will be this summation will not start from 0, but will start from 1. All right, so with the same reason that I explained to Cicera, then we change the, let's say we change the index that we are doing the summation over, because we don't like to work from n equal to 1 to infinity. We would prefer to work from m equal to 0 to infinity. So what we do, n equal to 1, we set it to be equal to m, and now we introduce these new variables in our calculation. When you do these new variables, you have to take away alpha and e power of minus I omega. And when you take that one out, then the entire expression is given by the coherent state at the time of t. So then what you will get, A acting on alpha will give you A times e power of minus I omega t times times the alpha. So we get a t is equal to alpha e power of minus I omega t alpha at the time of t. And if you do the complex conjugate, or let's say Hermitian conjugate, then you will get alpha t, alpha star e power of plus I omega t. Then the expectation value for x1 is 1 divided by 2 of alpha at the time of t of A alpha plus alpha at A dagger alpha, which this is given by 1 divided by 2 of this one will be alpha e power of minus I omega t plus alpha star e power of I omega t. Do you agree? And we assume that alpha is absolute value of alpha e power of I phi. If you set it here, then this is look like z plus z star. Z plus z star is twice of the real part of z. So this means that you will have alpha cosine of omega t minus phi. Okay. Huh, beautiful. Do you prefer to, yeah, that's fine. That's fine. Let's go with minus. It's fine. It's not a big deal. Is it clear? Isn't surprising? It is a little bit surprising because it's not zero anymore. I think that was what Manuel asked me as well in the break. So let's do the calculation for x2. For x2 will be 1 divided by, I'm jumping. For x2 will be alpha at the time of t. Then that will be 1 divided by 2i a minus a dagger. So can someone do the mathematics and tell me the result? We have already done the calculation.
Something similar to sign.
We decide, but let's do that. I mean, because we need really the coefficients. So that expression will be given by 1 divided by 2i. I will take it out. Then we do have alpha e power of minus I omega t minus alpha star e power of I omega t. This is look like z minus z star. Z minus z star is twice of 2i imaginary part of this. Okay, 2i goes away, then we will get absolute value of alpha, imaginary part of e power of minus I omega t plus I phi, which will be sine of omega t minus phi. Good. No mistakes, no minus sign missing.
Should that be phi minus omega t?
Phi minus omega t? Yes, thank you. Is that fine? Excellent. Thank you, Kyle. Good. It's showing up what we are looking for. It's already here. So for x1, we have this expectation value. For x2, we have this expectation value. So it's not anymore at the origin. It's somewhere else, okay? But still, I am not done with looking for uncertainty or variance. Now, from these relations, as a next step, I'm asking you to calculate x1 power of 2. So please do that. So find me x1 power of 2. Nope. I was close to doing a mistake. Who did? Do you agree? All right.
You forgot a square on the alpha star.
Oh, yes. Thank you. Excellent. Good. So now let's do the mathematics and find what is delta x1 power of 2, which is x1 power of 2 minus x1 power of 2. All right. We already did the calculation for both of them. The only things that we need to do is making a power of this, a power of 2 of these. So we will get essentially alpha squared e power of minus 2I omega t plus 1 plus 2 alpha squared plus alpha star power of 2 e power of 2I omega t with the positive sign, yes, and minus the other term power of 2, which is alpha 2 e power of minus 2I omega t minus alpha star power of 2 e power of 2I omega t. And the cross which is, I will write it down. So it's alpha alpha star. So it will be alpha alpha star plus alpha alpha star will be minus 2 absolute value of alpha power of 2. Okay? Do you agree? And then this term goes away with this term. This term goes away with that term. And finally, that term goes away with this. So we will get 1 divided by 4. Huh. Surprising. In a similar fashion, we will get delta x2 power of 2 also to be equal to 1 divided by 4. Okay, so I will let you feel comfortable with the mathematics that we have done and understanding it better, and then we will talk about the physics in a few minutes. All right, so when you are done with the writing, just let me know. We can discuss about the physics. Fine? Good, let's start. Okay, let's see what does it mean. I mean, having this sort of situation for this specific state of alpha. So we had alpha, which is exponential of minus alpha divided by 2 divided by 2. Summation of alpha power of n divided by n factorial square root of n, which this state has expectation value of x1, which is given by alpha cosine of omega t minus phi. We assume that alpha e power of I phi is the coherent parameter. And x2 is given by minus alpha sine of omega t minus phi. And we know that also n, expectation value for n, is given by alpha squared. So, which means that alpha essentially is given is square root of n. So, alpha, the coherent parameter is essentially will give you square root of number of photons, or mean number of photons. And on the other side, we know that there is an uncertainty for delta x and there is an uncertainty for delta x2, which both of them are given by 1 divided by 2, 1 divided by 2. Remember, this is in dimensionless quadrature. Okay, so is in x1 and x2, not in q and p. So looking at uncertainty principle between delta x and delta x2, we get that this is 1 divided by 4. So independent of alpha parameter, uncertainty is saturated, right? This is a very important concept. It's not look like a coherent, it does not look like a Fock state. If you remember the Fock state, delta for Fock state, a pure one, delta x1, delta x2 was 1 divided by 4, 2n plus 1, which was greater than equal to 1 divided by 4. Remember, I'm highlighting this just to remember. So that case was depend on n. here there is no dependency on alpha, and this is important. I found a state which this state always saturates uncertainty principle. Always will give me minimum uncertainty. And this state is coherent state. Look at the phase space. Look at the phase space, what we will get for the phase space. X1, quadrature, and X2. Remember, X1, the expectation value, and X2 are given by this relation. Okay? Depends on the time. For example, at the time equal to 0, right? At the t equal to 0, what I will get? I will get alpha cosine of minus phi, which is cosine of phi. And X2, I will get minus alpha sine of minus alpha, which is sine of phi with a positive. So at the t equal to 0, I will get alpha cosine of phi, alpha sine of phi. Agreed? Which means that I'm pointing a place here. What is the radius?
Alpha?
Exactly.
Modulus of alpha?
Modulus of alpha, which means that is square root of n average. So let's write that. So this is essentially alpha, which is square root of number of photons. Good? At the time equal to 0. What is happening at the time equal to, let's say, pi divided by omega? Okay? I can look at any given time. Let's look at the time equal to even pi divided by 2 omega. Is up to you. And this angle is phi, by the way. It is alpha cosine of pi divided by 2 minus phi. And that one is alpha or minus alpha sine of pi divided by 2 minus phi. Do you agree? So can you point me to the right place that I have these at the given time of t equal to pi or 2 omega?
$90 degrees clockwise from the original position.
How many degrees?
90 degrees clockwise?
90 degrees clockwise or counterclockwise?
Clockwise, I think.
Clockwise, yes. It goes here. You agree? All right. So what is happening? By time, this state is evolving, right? But is a specific point that is moving in the quadrature space, in the phase space. True? Good. Excellent. So this is the first thing that you should remember. For coherent state, it is depending on time and the position that you are pointing out to this for the state is evolving on a circle. Okay? Now concentrate on the time equal to 0. What is happening for that one? is it a sharp point or is a distribution?
The distribution. It should be distribution.
The distribution with which uncertainty?
1/4.
1/2.
1/2.
1/2. So what happens? This is not a point, it's a circle, right? Which circle has an uncertainty, and this uncertainty is given by delta x1, delta x2. Okay, so here, I'm sorry, I had to plot it in a proper way, but remember that is in the delta x1 and delta x2. Okay, usually people, they prefer to plot it in rotated coordinate. All right, so this is the concept of coherent state. So the coherent state pointed out somewhere not at the origin, outside of the origin, but then what it does, you have minimum uncertainty relation there. So you saturate the uncertainty principle there. All right. No questions? Excellent. Look at the concept. So this is rotating, right? This is rotating in time. And now we know very well that from x1 and x2, we can build up an electric field, right? We can get the electric field. Do you remember the electric field concept? So this is true for that we are doing for the simple harmonic oscillator, but we know that we found the Hamiltonian even for EM field, and we look at EM field, and each EM field is a electromagnetic field for that cavity that we consider is the combination of different polarization and different K vectors. So we assume that we are dealing only with one K vector and one polarization state. So if you remember, at that case, the electric field that we consider, electric field was given by, I'm writing the entire expression, sorry guys. So we wrote that as summation of K, summation of, I think we assume sigma. Then we had an expression, it was, I think, h bar omega divided by 2 epsilon naught v, power of 1/2. And then we had E of K and sigma. And we had A, E power of I. There was an I here as well. Oh, let's put the I here. Remove that expression. Okay. K dot R minus A hat E power of I K dot R. I think that was the expression that we found it. Right? And if we look only at one single mode or specific single one mode, which means that polarization is fixed, K also is fixed. We have one fixed K and polarization. Then electric field for that specific mode is given by with a coefficient, which for the time being I don't care. We have A minus A dagger. Of course, E power of IK exists and is a given phase, which essentially can be integrated in the phi that we had it in our expression. Oh, if you want to write it properly, let's write it properly. And just to clarify this, E power of I K dot R minus omega t, and then we had the phase, which is here, minus A dagger E power of I K dot R minus omega t with a minus sign. Okay, fine. Then we can look at the expectation value of electric field. And if you look at the expectation value of the electric field, that will be given by an expression that is plus is sine of k dot r minus omega t minus a phase of phi. Remember, this is our coherent state. And remember, in this picture, I use Schrödinger picture. Sorry, I use Heisenberg because the operator, they are time dependent. Heisenberg picture. In a Heisenberg picture, operators, they are time dependent. And states, they are time independent. The states that we consider, it's a coherent state that we assume, and there is no time dependency there. You can go with either way. It's really depending on you.
So then shouldn't the A and A dagger be like A at 0, A dagger at 0?
Yes, this at the 0. This is the reason that I had omega t here.
Okay, got it. All right.
Okay. But remember that alpha now is time independent. You can go with either way, honestly. You can go with other picture. You can omit omega t here and just look at the case when the states that are time dependent. I mean, it's an exercise you can do either way. The physics is the same. Okay. What I want to tell you is that electric field, expectation value for electric field is very similar to one of the quadrature, which is the x2 quadrature. All right. And we know that is oscillating in time and space. Let's fix the space and look at the time. So classically, if we are watching the time and we are looking at the electric field, and remember always that there is an alpha at the front, right? Because due to the A and A dagger, we do have a coefficient of alpha at the front, which this alpha will give you the magnitude or the strength of the coherent state. So always start from an alpha, of course, with the normalization factor, goes to minus alpha with the normalization factor. Okay. And these start to oscillate from specific phase situation. The oscillation comes from the fact that you have this step, k dot r minus omega t minus phi. So phi will define the set that you start with, and k dot r minus omega t starts the oscillation. So now let's look at the time oscillation, not at the space. So fix r equal to 0, and you are looking at the electric field which is oscillating. Surprisingly, this does not look like vacuum, which will give you 0, but it starts from a certain point. So it has magnitude, is oscillating. Okay? But we know from delta x1 and delta x2 that there is an uncertainty in the magnitude here. All right? Because these look like delta x2. And this magnitude will be something like that, that is giving us uncertainty in the value of this. This is what you have for coherent state. All right. if I want to help you to understand and imagine what is going on, do you remember the quadrature for x1 and x2? We say that the state is rotating on a circle, right? This was x1 and x2. And the circle has an uncertainty. So this is what the field is oscillating. By time, this is oscillating, right? It goes, the state is evolving from here to here, to here, to here, to here, and etc. at any given time. Now, if you project it on one direction, assuming that there is a, let's say, a projector here, which you look at the shadow, okay? If you look at the shadow, I mean, this is the projector, assuming that there is a lamp here. Now, let's be a little bit creative. Oh, let me make that. So I have a lamp here. And then what it does, you project these on x2. So there is a projection here, which that projection will give you the uncertainty that you have it for delta x2. When it comes to the time equal to, let's say, pi divided by omega, then the projection will be here. When it goes to the origin, that's the region that you have this uncertainty with this dimension. Are you following up the conversation? Excellent. So this is what happens. So you have a phase representation, but also on the top of this, you can look at the uncertainty principle and you can look at the electric field component. All right? Good. So this is the property that we have it for coherent state. Now, assuming that you are changing the magnitude of alpha, what is happening? The radius will enlarge. We'll go to higher one. So consequently, then this starts from a higher value, right? With the same frequency, of course, it starts to oscillate, but it starts from a different, let's say, amplitude. So, but in any cases, the uncertainty that you have it in delta x1 and delta x2 is 1 divided by 2 for all of those cases. And this is important. All right. Now look at the Fock state. Look at the case that we have, the Fock state. So Fock state, do you remember the delta x1 and delta x2, they were equal to 1 divided by 2, 2n plus 1, power of 1/2, 1 divided by 2, 2n plus 1, power of 1/2. And what was the x1 and x2 for both of them? They were 0. Right? So look at the case of vacuum, n equal to 0. For the vacuum, what we were expecting, what we were expecting, we say that it starts from 0, but the uncertainty that we do have, it's like 1 divided by 2, which is something like that. We have delta x1, delta x2 that is equal to 1/2 for both cases. If you look at the electric field oscillation, the mean is 0. But if you place, let's say, if you look at the projection of that, then you will see that there is an oscillation here. There is an uncertainty. Okay? Which this uncertainty is given by the value that we have it here. For n equal to 1, If I want to oscillate, I want to have the oscillation, I will say that oscillation goes like that with the same frequency. Oscillation goes like that with the same frequency. Oscillation goes like this with the same frequency, and etc. So you have all of those possibilities for different phases. That's the reason that you cover the entire of those region. It now look like a coherent state, which starts from specific phase. Okay? And the same scenario happens for n equal to 1. For n equal to 1, what do you expect, guys? Do you expect the amplitude will be higher or lower?
Higher amplitude?
Absolutely. So this is what happens. So the average again is 0, but the region that you cover is higher by the value that we just derived that. So it will be essentially 2 times 1 divided by plus 1 divided by 2. So essentially it goes to be higher region, which means that the field oscillation starts from any of those possibilities. So it starts from here, but also has the possibility that will start from this region, or start from this region, or start from this region, and etc. So you have the entire dot space, which you do have uncertainty about the starting for the electric field. All right? And n equal to 2, the same scenario. So while the coherent state, it seems that what it does, it shifts the number states or vacuum states, depending on really the definition that you want to go for. Let's say that the vacuum state, it shifts the vacuum states because the vacuum state has minimum uncertainty principle and brings it somewhere else. Okay? So vacuum state that we had for n equal to 0 had minimum uncertainty, and it was in a certain region. But for coherent state, what we have a phase space of x1 and x2, which it seems that that coherent state has been displaced and brought to somewhere else. Okay? Because the uncertainty principle that you have for coherent state and for the vacuum state, they are all the same. So it's a delta x1, delta x2, which is equal to 1 divided by 4, but has been displaced. And how much has been displaced? By absolute value of alpha, by square root of mean photon number. Okay? So this is the reason that we call coherent state a displaced vacuum. By the way, I recall just last lecture I wrote vacuum with the double C instead of double U. Okay, so coherent state essentially is a displaced vacuum. How much is displaced? By absolute value of alpha. Okay, and the phase, of course, is given by phi that we discussed. So this is what we call it, coherent state. Clear? Hamiltonian, I mean, honestly, I write it down and then we can discuss about the physics. I mean, Questions?
Yep. I have
Yes,
a question.
Manuel.
Can you displace a non-vacuum state?
I have not displaced non-vacuum.
No. Is it possible?
Yes, of course. You can displace a coherent state, right?
Mm-hmm.
No problem at all. You can displace a squeeze state. Is an operator. Or you want a photon number to be displaced. Manuel.
I want a Fock state that is not the vacuum displaced.
Yeah, you can do that.
It's just the displacement times. I mean, displacement operating.
Yeah, mathematically you can do that. You can do d alpha acting on one.
Yeah, mathematically, yeah, but is it like, does it have like a meaning in physics?
Wait for your either for your assignment or for your midterm.
Or
okay. Good. I like the way that guys you are thinking. It's excellent. It's excellent. It's exactly the way that I expected. Any questions, or you're okay?
I had a question.
Yes.
So just now we saw that this like x2 operator, the sort of analog you can actually measure would be the electric field.
Would you please repeat again? Sorry.
Oh, okay. Maybe clear. The electric field sort of behaves like this x2
yes
operator.
Yes.
And would the magnetic field behave like x1?
In a way. The magnetic field. So the magnetic field will be given by the operator that we had. So it was k cross the vectors. So if you assume that they are orthogonal to each other, no.
No?
No. In terms of oscillations, yes. But in terms of direction, no. Because that should be orthogonal to each other. Look at the quadrature is look like X and P is not look like the magnetic field and electric field. It's a little bit confusing if you go in that direction. Okay.
So is there a way to physically measure x1 and x2 for?
Yes. People we do with the Homodyne detection. We will discuss about that. Homodyne detection will give you the possibility to measure, but this is what people they do with squeeze state. So when we do squeezing, you have to understand what you are doing what you do. Are you squeezing the amplitude or the phase? And then it means that you have to perform some sort of measurements. Okay, and this measurement is done with Homodyne detection. We will discuss about that. Absolutely.
Thanks.
Of course. Good. So there is an operator essentially. I mean, there is a physical phenomena which does this, and this squeezing happens. This generating coherent state happens naturally in laser cavity. So if essentially you have a laser, this process happens inside of a laser. Inside the laser cavity, you do have displacement operator. And this displacement operator essentially is created from a Hamiltonian. So is e power of, again, the same usual process that we have. So you go from a Hermitian operator to unitary operator, which is minus I divided by h bar acting on Hamiltonian, which is Hamiltonian is the interaction Hamiltonian. And interaction Hamiltonian for creating a coherent state is given by, let me remember, differently it has h bar. You do have a g, g star a dagger minus h bar g a, if I recall well. It should be Hermitian, so if I look at the I, yeah, it should have an I as well, because it should be Hermitian. Okay, and G is the coupling, of course. H bar goes away, goes that one. Okay, yeah. So then this means that you have e power of minus I divided by H bar, I H bar times G star A dagger minus G A. Someone can look at the display. I think it should be, yes, just should be the same. Yes, okay. It should be power of G star A dagger minus G A. So in our calculation, we assume that G is given by alpha. So that is e power of alpha star A dagger minus alpha A. Okay. G is the same as alpha in our calculation. Is a coupling essentially. So this is what happens inside of a laser cavity. So you have this interaction Hamiltonian, and when you have such interaction at any given time of t, then you have this unitary operator, which the unitary operator is given by displacement of alpha. Essentially, I have to multiply everything by time. So that is time, then it is gt, and that is g star t. That's the reason that gt is alpha. So yeah, now I think I feel comfortable with that. Let's me rephrase it in a proper way. So that will be g star t A dagger minus gt A. Then we define that g star t is equal to alpha, and then that will give us the displacement operator of alpha. And remember, the displacement operator of alpha will take any state and moving around. So in this case, it takes, if acts on the vacuum, then it brings it from origin to any other given place, which the radius is given by alpha, and the place, the orientation is given by phi, which alpha is alpha e power of I phi. Okay. So you can have d alpha acting on d beta on vacuum. What it does, we are displacing vacuum twice, one with beta magnitude, or let's say beta parameter, the other one with alpha parameter. So the outcome will be, so
physically you do that by having like two laser cavities right next to each other?
You can amplify this again. Yes.
Okay.
Which is fitted with a coherent state again. Yeah, the first one creates and then you amplify. This is what you will get. You have vacuum. First you displace it to beta. Okay, this is beta, and the angle is phi beta, and then you get beta state, and then you do another displacement to alpha. Okay. Okay. So this is essentially what we have for the coherent state. And don't forget that uncertainty principle in any of those cases will give you will be minimized. It will be saturated. So delta x1, delta x2 always is equal to 1 divided by 4. Okay. As an exercise, guys, I mean, since I cannot cover the entire those calculations, I will ask you to do this to do similar calculation for squeeze state. Okay, here we are dealing with only annihilation and creation operator, which is wild group. You can build up another group which is the eigenstates. Oh, let's say not eigenstate. Let's go with this operator, which is operator of the squeezing, is 1 divided by 2 of zeta star a dagger power of 2 minus zeta a power of 2. Let's call that squeezing operator. Okay, and do the mathematics at home and look at the S acting on vacuum and S acting on coherent state. Okay, so I introduce you squeezing operator. Remember, this is a Gaussian operator. Sometimes some people, they call it Gaussian operator. We are not dealing with A and A dagger. We are dealing with A power of 2 and A dagger power of 2. And again, zeta, which is squeezing parameter, is given by a zeta e power of I, let's say chi. Okay? Or let's call it theta because I introduced. So now I am asking you kindly to take two different states, vacuum and coherent state, and look what is going on with squeezing operator acting on vacuum, squeezing operator acting on coherent state. And from these two, find out what is delta x1, what is delta x2. The same scenario here. Find out delta x1, delta x2. We want to look at the uncertainty principle for these two. So next lecture, I will not talk about how to drive those equations. I'm sure that you can do that. Use Baker-Hausdorff lemma, because it's the way that people they can do the mathematics easily. What I drive, I explicitly write delta x1, delta x2, which I'm expecting you to already have that for both cases, for S on 0 and also for S on alpha. And we discuss about the concepts. We discuss about the physics. It will take about half an hour, and then we move to the probability distribution, and hopefully next lecture we will finish the probability distribution as well. Clear? Good. I will stop the video. If you have questions, we can discuss now.